So after Copernicus comes Brahe, Tycho Brahe, and I think there was like a 3-year overlap where Copernicus was still alive and Brahe was born. So when I think of Tycho Brahe, I think of nobility, somebody who had some money and had fancy toys because he had money. And that's a whole nother story about if you have money, you can take your education where you want it to go. No money, not so much. So anyway, you see here kind of his fancy lab. Tycho Brahe was, I don't know if it was an amateur astronomer or an astronomer, and he made impeccable notations of how he saw movement in the nighttime sky. Actually, Tycho Brahe is somebody who observed a supernova and recorded it. So the thing about Brahe, though, is he wasn't as much of a scientist. How to think about the data actually came and is attributed to Kepler. So Tycho Brahe hired Kepler to look at his data. One thing about Brahe is he still could not anticipate where the planets would be. And the other thing I mentioned, stellar parallax in the previous section, he could not see any stellar parallax. He could not see stars moving amidst the background stars. And so he said, well, the Earth must be standing still. The other planets are orbiting the sun, but the Earth must be standing still. So Kepler actually looked at Tycho Brahe's data. And when he looked closely at Brahe's data, Tycho's data, what Kepler found is that if you go ahead, and I've been kind of talking off and on about this circle thing, that, nature is perfect, a circle is perfect, therefore nature must work in circles. If you go ahead and take that shape and elongate it to, looks like kind of an oval, then you can go ahead and anticipate where the planets are going to be. You can anticipate all sorts of things. Okay, so that's what Kepler did. And a good scientist will look objectively at their data and think outside the box, and that's what he did. So instead of being a circle, actually circle is a special type of what we call an oval or an ellipse. So you see them side by side from left to right. Left is a circle, right is an oval, or specifically an ellipse. The thing about ellipses and a circle is they have what we call two foci. The thing about a circle is those two foci overlap. But you kind of see as you get the oval, sort of take a circle and kind of elongate it, you begin to see your two foci that overlap with the circle. With an ellipse here, you see a major axis this way, the long way, and a minor axis this way, the short way, okay? And you see the two foci here, kind of where the nails are. That's actually how you can make an ellipse, by cementing two nails or thumbtacks and then taking a piece of string and not changing this piece of string, kind of drawing a line or drawing a circle around, or, going around it. So one other thing about ellipses, because we're going to talk more in astronomy about ellipses, is that they have a degree of eccentricity. You can see at the bottom there. So their eccentricity ranges from 0, not eccentric at all, to 1. So eccentricity of 0 would be a perfect circle. The more flattened out it gets, we say it becomes more and more eccentric. So Kepler is attributed to looking at the movement or motion of the planets and understanding with the heliocentric model, the sun at the center and the Earth orbiting the sun and the planets also orbiting the sun. He came up with 3 planetary laws. The first is that the Earth and the other planets orbit the sun in an ellipse, a shape called an ellipse. And so just to kind of show you how that works, we said that ellipses have 2 foci, and actually the sun is located at one of those 2 foci. There's nothing at the other foci, although I want to visit it. Okay, I think we've looked at these terms before, perihelion and aphelion. Perihelion is when the planet or the Earth is closest to the sun, and aphelion, and you can kind of see how this works because the sun is kind of off-center from the orbit of the planets and the Earth. Aphelion is when the planet, the Earth, or a planet is farthest from the sun. So, and remember we talked about this when we talked about seasons. Actually, perihelion happens in winter, about January 3rd, and aphelion happens in July, okay, about July 3rd. So Kepler's second law of planetary motions is that as a planet, and it's counterclockwise, as a planet orbits the sun, they will speed up when they're near perihelion and slow down when they're near aphelion. And, excuse me, I have a kitten crawling on my lap. So if I were to use this, my voice as kind of showing you how fast I'm going, okay, so it goes kind of like this. At aphelion, it's going slowest. Slow. Okay. So it goes, you get the idea? So the way that works then is if we were to call this segment A, okay, well, let's call this segment A. Call this one segment A, or location A in orbit, and this is location B in orbit, okay, and this is location C, and this is location D, okay. The time it takes the time it takes for the planet to orbit or to complete that segment at perihelion, I mean, for the same amount of time it goes farther, okay? Out here at aphelion, okay, the same amount of time it goes, it covers less of a distance. So the time that for segment A to B and segment C to D is the same. So the whole equal areas swept out in equal times is this. If you take those locations and go back to the sun, okay, this area, okay, is equal to this area. And that's it. Okay, so that is his second law. Oops, I wonder if he needed those words. So Kepler's third law is, to me, a little bit the most confusing. But we do this all the time in science when we are measuring multiple characteristics of, in this case, a planet. So if you look at two characteristics of the planet, if you look at the planet's time it takes to complete one orbit about the sun, okay, that's P, and if you look at its average distance from the sun, that's A. And if your period it takes to complete one orbit is in years, okay, and if its distance from the sun is in units of astronomical units, then you can square the period and cube the distance, and they're equal. Okay, we do that all the time. So here are kind of side by side for all the planets. Ooh, Pluto, well, maybe not. An extra bonus, wow, one dwarf planet. Okay, there's how long it takes them to orbit the sun, period, and there is their average distance from the sun. So over here, use a spreadsheet to do this. Basically, we square the period and we cube the average distance from the sun, and notice how like dead on they are. So that's actually his third law. So this actually you may or may not have access to. These are some like little applets to kind of play around with Kepler's three laws.